lesson is about the term differentiability just means you can take the derivative of it. If something is differentiable, you can take the derivative of it. So, we're going to talk about a derivative and look at what the graphs of the derivatives would look like. So let's say that we have a graph of f of x right here. And this f of x takes on the shape of this line right here. And let's just say that this is y equals x plus 2. And we want to know what the graph of the derivative is. So we want to know what the graph of f prime of x is. Or y prime. I didn't call this f of x, it's called a y prime. Well, what do we know here? What is the derivative of this? Well, if we use the shortcuts, we get 1 times 1 is 1, and this becomes x is 0, so it's just 1. Y prime is 1. Or you could think about it as, hey, this is a line. What's the slope of that line? What's the m value? So it's 1. So either way you want to think about it, that's what you get. So we're going to graph the slope of this function here, and the slope of this function here is, every place, this has a slope of 1. This has a slope of 1. This has a slope of 1. Every point on that line has a slope of 1. So the graph of the derivative of it would look like that. That would be the graph of the derivative. Now, notice some characteristics here. Characteristics here are, okay, this green line is positive everywhere. It's got positive y values. Well, the line has positive slopes everywhere. So that's what we're looking at. Now, that is a basic one. Let's look at a little bit more involved problem here. Yes?
Can I just put one thing? Like F and C says that's good enough?
A little bit more going on than just that. I mean, you get partial credit possibly, but okay. So we've got f of x equals, let's go with x squared plus 2. Now, what do we know that the derivative of this function is?
2x.
Yeah, f prime of x is just going to be 2x. Well, I'm going to circle that in green because I'm going to graph its derivative in green. So think about it like this. Let's just graph both of them. X squared plus 2. We're sitting here. We got a parabola, right? The parabola is here and here. So graph its derivative. Its derivative is 2x, which is a fairly steep line. There are steeper lines out there, but it's a fairly steep line. So if you think about it, you know, what's happening with this graph right here in the second quadrant? It's decreasing, right? Well, if it's decreasing, then the derivative value should be corresponding to negative numbers. So we're getting negative numbers right here for our slopes because every y value down here is negative. I also notice that it's steeper out here than it is right here. So the negative values here would be lower than the negative values here. It decreases the slope till it hits 0. Well, that's just happens to be where we cross the axis with our slope of our derivative, or with our graph of our derivative, I should say. So this is f prime of x, and this is the graph of f of x. So we're looking at those different combinations right there. Now, let's look at by y equals the absolute value of x plus 2. Okay, so y equals the absolute value of x plus 2 is a v, and it crosses, or its vertex is right here. Now, what does the graph of its derivative look like? Well, what is my slope everywhere to the left of that dotted line?
It's a negative slope.
It's a negative slope, but it's a negative constant slope, right? What would that slope be? Just looking at it graphically.
Would it be just 1?
Negative 1, yeah. It'd be negative 1. So I'm here. Well, hold up. Negative 1's probably closer up to here. So I'm here. Now, what about once I hit to the right?
Positive 1?
Yeah, it jumps up to positive 1. Now, I have an open circle at both points right there. Because what we're going to see here is that at x equals negative 2, this function is not differentiable. We cannot take this point right here, we can't take the derivative of it. Because the slopes everywhere here, if you think about its continuity, slopes here are all negative 1, slopes coming in from the right are all positive 1. So we're not, if we're thinking about as far as a limit's concerned, we're not approaching that same number. So this function right here is not differentiable at negative 2. And it does that little number right there. So, what can cause a function not to be differentiable? What can cause a function not to be differentiable?
Anything
Well,
that changes the slope.
Well, these slopes change too. Those slopes change. It's differentiable everywhere. Graphically speaking, we're looking at a corner or a cusp. Corner or a cusp. So here we have a corner. A cusp would look something more along the lines of this. So in a cusp, as you approach that value coming in from the left and the right, the derivatives will be approaching negative infinity in one direction and positive infinity in the other direction. See, these would all have positive slopes over here. So as we get closer in here, these would be getting closer to positive infinity. These would be getting closer to negative infinity. So we get a cusp out of that. So corner or a cusp is one place. A second place that we could be not differentiable is if we had a vertical tangent line. A good example of that is f of x equals the cube root of x. F of x equals the cube root of x would take on that shape right there. So if you do the derivative and plug in 0 there, you would get an undefined value. So we say that if we have a vertical tangent line here, which I didn't draw it great, it'd be a little bit more like that. but it's just at that one instant at 0 that you have a vertical tangent line. So that function would not be differentiable there. At an endpoint, we won't be differentiable. So y equals the square root of x. Y equals the square root of x. Or here, we go up here, we've got an endpoint there. It's not differentiable at that endpoint. And last of all, if the function is not continuous there. So if the function is not continuous there, and we talked about continuity. Continuity, where is it continuous? F has to be defined at that value. The limit has to exist at that value, and the limit has to equal to that value. So it could be discontinuous because it's not defined there. Several different things that would keep it from being continuous. But these are reasons why graphically we would see that a function would not be differentiable at a particular point. Now, based on that, I can look at the, well, let me start another video.